This conference will now be recorded.
Good evening, everyone. Am I audible? So, yesterday we have discussed about the interrupt, like what is interrupt, different types of interrupt, what are all the sources of interrupt. Whenever there is an interrupt, what the controller will do, like different interrupt handlers are there, our controller is following the ISR method, like that we have discussed. And all the sources of an interrupt, it will be having its own flag bit, its own enable bit will be there, and we will be having a GIE bit which is for all the peripherals as an interrupt. Like that we have discussed what all the bits are associated with the interrupt. So we know that when it comes to an interrupt, any internal peripherals or the external peripherals can generate the interrupt. So now what we are going to do, we are going to program for the external interrupt. Okay, we are going to program for the external interrupt, which means outside the microcontroller, I'm going to pick one peripheral, okay, and I'm going to program that peripheral as an interrupt. Okay, so yesterday we have discussed with one slides, right? Let me open that slides. Yeah. So here on our microcontroller board, we are having one switch. On our microcontroller board, we are having one switch, and that switch is connected to the RB0th pin. So this, with the help of this switch, we can program for the external interrupt. We'll discuss whether only one switch is available or can we program the other switches. About that, we'll discuss. So on our microcontroller board, we are having one switch. The switch is connected through the RB0th pin. We can use that switch as an interrupt. We know that we have a digital keypad switch connected to the port B, right? We are going to program that switch as an interrupt. But before that, can you tell me, like, whether the switch is connected through a pull-up circuit or pull-down circuit? Pull-up circuit or pull-down circuit? Yeah, it's connected on a pull-up circuit. So with respect to our microcontroller, okay, so we have one switch, okay, and the switch is connected to a pin called RB0th pin, and it is connected on a pull-up circuit. So since it is a pull-up circuit, okay, either here we can press the switch or we can release the switch. We can press the switch or we can release. Whenever I press, pin value will be 0, and whenever I release the switch, pin value will be 1. Whenever I release the switch, pin value will be 1. So whenever I press, falling edge will occur, and whenever I release, rising edge will occur. Whenever I release, rising edge will occur. This is about one switch which is connected to the RB0. Now we are programming for the external interrupt. So whenever we are programming for an interrupt, we should know if we are using a peripheral means that peripheral, it will be having its own flag bit, its own enable bit will be there, right? So now how to refer that, where the information will be available. So all the bits, it will be available inside a register. All the registers are inside our microcontroller. So we have to refer the data sheet. So in the data sheet, it will be available on page number 155. Let me open the data sheet. On data sheet page number 155, we will be having the introduction about the interrupt. So with respect to our microcontroller board, PIC16F877A microcontroller, it is totally, it supports 15 sources of interrupt. How many interrupts are there? 15 sources are available. So on our external interrupt, on with respect to our microcontroller, total 15 sources of interrupt is available. It's like a combination of both external and the internal. Overall we are having 15 sources of interrupt, which means for all the 15 sources separate 15 flag bit will be available and a separate 15 enable bit will also be available. All the sources will have its own flag bit and its own enable bit will be there. Now importantly we are going to concentrate, okay, we are going to concentrate on the external interrupt because I am programming the external interrupt. So in order to know about this external interrupt, if you scroll down you will be having the information. So external interrupt is available on RB0th pin. So in the very first line itself they have mentioned only one pin. Okay, so with respect to the external interrupt, it is available on only one pin called RB0. Apart from RB0 we cannot use any other port pins in order to program as an interrupt. Okay, so with respect to our microcontroller, RB0 only one pin is available for the external interrupt. To that pin you can connect the peripheral and you can generate the interrupt. So only one external interrupt pin is available. More than that it is not possible. Our controller is not supporting that. Now we know that we have some 6 digital keypad switches. All the digital keypad switches are connected to the port B. Pin numbers are from RB0 to RB5. Now, can we use, apart from RB0, we will be having the remaining 5 digital keypad. Can I use the remaining 5 digital keypad switches as an interrupt? Apart from RB0, can I use the remaining 5 digital keypad switches as an interrupt? Apart from RB0, can I use other 5 switches as an interrupt? Is that possible? No. Why? Because our microcontroller itself, it's mentioned only RB0 it will support. Apart from RB0, whatever the switch is connected to any other pins, that will not be supported. So it will support only the RB0 the pin. Now, under the pin is also edge triggered, which means to that switch we are connecting one switch, right? That switch we cannot program for the level. It is of what? It is of edge triggered. It is often edge triggered. Okay, it is often edge triggered. And here you can configure like when I need to generate the interrupt. Whenever I press the switch, I want to generate the interrupt, or whenever I release the switch, I want to generate the interrupt. Like that, you can configure, you can select the edges. Okay, level is not possible, but edge is possible. But in case of an edge, falling edge and rising edge will be there, right? Which one is edge triggered? RB0th pin. That whatever the external interrupt you are connecting to that RB0 with the help of the pin only you can mention what type of triggering it is, right? External interrupt is RB0 only. To that RB0 I will be connecting one pin. Sorry, I will be connecting one peripheral, whatever the peripheral can be. But the RB0, the pin is edge triggered. Okay, you can program the pin on only on the concept of edge triggering. Level triggering is not possible. Even though it is an edge triggering, two different edges are there, rising edge and falling edge. At which edge I want to generate an interrupt, that also we can configure. On which edge we have to generate or the interrupt has to be generated, that also we can configure. In order to select the edge, we are having one edge selection bit. INT EDG edge selection bit is available. So whenever you want to configure, you want to generate an interrupt on rising edge, then what you have to do, you have to set to the int edg bit as 1. Or whenever you want to generate an interrupt on a falling edge means, then int edg bit you have to make it as 0. So now the RB0th pin is available only for the edge triggering. So in order to select the edge, okay, edge selection bit is available. Okay, in order to select the edge selection bit is available, and the bit is nothing but int edg bit. Whenever you set the bit as 1, interrupt will get generated on the rising edge. Whenever we clear the bit as 1 bit to 0, then the interrupt will be generated on the falling edge. So at which edge the interrupt has to be generated, like that we can configure, whether rising edge or falling edge, that we can select. In order to select that only, we are having this edge selection bit is available. Now all the sources of an interrupt, it will be having what, interrupt enable bit, interrupt flag bit will be there. So in order to know about the flag bit, here itself it is given, whenever a valid edge appears on our pin. So if you are programming for a falling edge means, whenever there is a falling edge, okay, whenever there is a falling edge on the RB0th pin, the corresponding flag bit INTF, the bit will be set as 1. If we want to program on a falling edge means, whenever there is a falling edge occurred, interrupt will get generated. So whenever the interrupt is generated, what the hardware will do, the hardware, it will set to the flag bit as 1. And what is the flag bit, INTF is nothing but the interrupt flag bit. So here we are having the interrupt flag bit, and the bit is nothing but int, f is nothing but the interrupt flag bit. So whenever the edge appeared, the intf flag bit, it will be setted by the hardware. That we know, flag bit, it will be always setted by the hardware. And what we can do, we have to clear that flag bit in the isr. We have to clear that in the software. We have to clear the flag bit in the software. Why we are clearing, otherwise again and again isr function will be called continuously. To avoid that, we will be clearing the flag bit. Now the interrupt can be disabled by clearing the enable bit INTE. So we know that all the sources of an interrupt will be having its own interrupt enable bit. So here we are having the interrupt enable bit. That enable bit is nothing but INTE. So whenever you set the bit as 1, now RB0, okay, will be enabled as an interrupt. Okay, RB0 will be enabled as an interrupt. If the INTE bit, if the interrupt enable bit is 0, which indicates RB0 is disabled as an interrupt. Okay, so whenever you want to use a peripheral as an interrupt, we have to enable the enable bit. So if you want, you can enable. If you don't want to use the interrupt, you can disable that bit also. Okay, so when I want to program for an external interrupt, we are going to use the 3 bits. We are going to use the 3 bits. Along with that, GIE will also be there. That is mandatory for all the type of an interrupt. Is the introduction, is the about the external interrupt, is that clear for everyone? Make a note of this. If you are having any doubts, please post your doubts on the chat box. No, no, all those that I have taken, for example, I have taken. Okay, in order to make you to understand, for example, I have taken, that is not the exact bits. If you want to know about the exact bit means, we have to refer the data sheet. So in the introduction, I have taken all the bits as an example bit. Apart from GIE, GIE is the proper bit, enable bit or the flag bit or the priority bit, all are example bits I have taken. Okay. Everyone, have you noted this? Have you guys noted this? Okay. Now, based on this, we'll write one program. So now I'm going to write a program to toggle the LED, okay, to toggle the LED on interrupt. So whenever the interrupt is generated, I want to toggle the LED. So now here, I am going to use one LED because I need to toggle it, right? So I'm going to use the RD0th LED. Then I am going to use one switch which is connected to the RB0, but this switch I am using the switch as an external interrupt switch. I'm going to use the switch as a external interrupt. So now we have to configure the external interrupt. Excuse me. So in order to configure that external interrupt, I am going to take one function called external interrupt.c. External interrupt.c. I'll be configuring the interrupt. Then I'll be having main.c in order to implement our logic. And whenever there is an interrupt, controller will call the ISR function. We have to write the logic for the ISR, right? That I'm going to take it in a file called isr.c file. Okay, so now we'll start with the coding part. So now here inside this external interrupt.c file, I am going to take one function, init external interrupt function. So why I have taken this function? Here we will be configuring the external interrupt. Okay, we have to configure the external interrupt. So what are all the things we have to configure? Okay, so now by referring the data sheet, we noted the bits. The first thing is we have to select the edge. We have to select the edge, whether rising edge I want to program or falling edge I want to program. We have to select the edge. Now let's say since the switches are connected on a pull-up circuit, whenever I press the switch, falling edge will occur. Whenever I press the switch, falling edge will occur. So here I am going to select the edge as a falling edge. In order to select the edge as a falling edge, int edg bit, we have to make it as 0. So now here on which edge I am programming? I am programming on a falling edge. So in order to select the edge, we have a bit called intedg bit. The bit we have to make it as 0 in order to select the falling edge. And with respect to the flag bit, we don't need to do anything. It will be automatically set by the hardware itself. The next bit is nothing but the enable bit. So in order to use the RB0 as an interrupt, the INTE bit, we have to make it as 1. So what we have to do? We have to enable the RB0 as interrupt. So in order to use that as an interrupt, we have a enable bit, int e bit is available. The bit we have to make it as 1, interrupt will get enabled for the RB0. Okay, so now here external interrupt is configured. So like only 3 bits are there for the external interrupt. Among that, flag bit, it will be set by the hardware itself. We don't need to do anything. So only 2 bits are there. Both the bits I have configured. Do you have any doubts here? Yes, GI is pending. So when it comes to the wiring concept, okay, when it comes to the wiring concept, first what we will do, we will be giving the wiring, then only, okay, we will be giving the wiring, then only we will be turning on the mains. The same thing, first we will configure all the peripherals, then we will be turning on the GIE at the last. There is no IO for the which means, are you talking about the direction, Shibun? There is no direction, it will be like, already it is a by default, it will be like an input only. You don't need to set any separate direction for the external interrupt. Okay, so now we'll move to the main function. Which 1 or 0 are you asking? This 1 or 0? Are you talking about this? Yeah, it will be just for enable or disable the peripheral as an interrupt. Correct. Okay, fine. So now we'll move to the main.c. So here the first thing we will be having is our init config function. Okay, because we need to configure the LED and all, right? So here let's say I'm configuring the LED. So we have to set the direction for LED as output direction. So in order to set the direction, I am using the trisd register. So in order to set the direction as output, we have to assign the value 0. And initially, I am going to turn off the LED. Okay, in order to turn off, what we have to do? Excuse me. In order to turn off, what we have to do? To the port D, we have to assign the value 0x00. Now we have configured the LED. So we have to configure the external interrupt. So to configure the external interrupt, we have already written a function. So just I'm going to call that function. So if I call that function, external interrupt will get configured. Function call will happen, the things will get configured. Now we have configured all the necessary things. So at last we have to enable the GIE. So in order to enable the GIE bit, we have to make it as 1. So we can use the interrupts now. So we have configured all the other things. So after configuring that only, we have to turn on that enable. That's why I said you don't need to set any direction for the external interrupt. It's not a switch, right? It's an external interrupt now. If it is polling, then you can set. Okay. So now then followed by the init config. Yeah. Followed by the init config, we will be having the main function. Inside this main function, first we have to call the init config in order to configure the peripherals. Then the logic we will be implementing inside the while one. We'll discuss about the while one later. First we'll understand about this ISR function. Now, whenever the interrupt is generated, who will call the ISR function? Who will call the ISR function? Microcontroller will call. So, whatever the function name is there for the interrupt ISR function, that function name you should not give any other name. So, this is the default function name for the ISR, underscore underscore interrupt space ISR. Okay, this is the function name for our ISR function. You should not give any other name to the ISR because You are not calling. Controller only it will call the ISR. So controller will know only this function name for the ISR. So we should not give any other function name. This is fixed. This is by default. So inside the ISR, what we have to do? We have to check whether the RB0 is generated the interrupt, whether the RB0 is generated the interrupt or not. So how will you check that? With the help of the flag bit. We are having the flag bit, right? So if that interrupt int interrupt flag bit, whether the flag bit is set as 1. If the flag bit is set as 1, interrupt is generated because of our RB0 to switch. So before coming out of the interrupt, what we have to do? We have to clear the interrupt flag bit. This we know. So whenever I press the switch, whenever there is an interrupt, I want to toggle the LED. So I have taken RD0th LED. So here whenever the interrupt is generated, I'm going to toggle the RD0th switch. Whenever the interrupt is generated, I'll be toggling the LED. So here what will happen? So here itself I have toggled the LED, so I don't have any other logic to implement inside the while one. So I'm just terminating it with the semicolon. So here how the execution will happen? So what our microcontroller will do, it will be executing the while one continuously. Whenever I press the switch, falling edge will occur. Whenever I press the switch, falling edge will occur. Whenever there is a falling edge, then the hardware, it will set the flag bit as 1. Okay, so controller will be executing the while one. Whenever the RB0 switch is pressed, okay, what it will do? It will generate the interrupt. How it will generate the interrupt? By setting the interrupt flag bit as 1. Whenever the flag bit is 1, the microcontroller, it will call the ISR. Inside the ISR, we are toggling the LED. Inside the ISR, we are toggling the LED. Once the ISR is completed, again the microcontroller, it will return to the while one. This is how the execution will happen. So microcontroller will be executing the while one whenever we press the switch. Okay, whenever we press the switch, which edge will occur? Whenever we press the switch, which edge will occur? Falling edge will occur. So whenever there is a falling edge, interrupt will be generated by setting the flag bit as 1. Whenever the flag bit is 1, microcontroller will call the ISR. Inside that, we are toggling the LED, we are clearing the flag bit. So once that is completed, once the ISR is completed, the controller, again it will return back to the while one. So it will execute the while one. So this much is the programming for the external interrupt. Is the program is clear for everyone? Do you have any doubts here? Why we need to disable the GIE? Why I need to disable the GIE? To avoid recursion. Very good. But yesterday I explained that. Did I mention I have to, we have to disable that? Can you please refer your notes? To avoid the recursion, who will disable that? Microcontroller only it will disable. Do I need to disable? No, automatically controller will do. Clear? Others, do you have any doubts in the programming? Is the programming is clear? Others, can you please respond? Okay. So now the same code is available in our template program. We'll open that, we'll execute and we'll check the output also. Okay. So it is available under second folder, which is folder here. The name is for interrupt sources. So the very first program, external interrupt. Open that project, external interrupt project. So let me set the project as a main project. We'll open the code and we'll check. Okay. So external interrupt.c, isr.c, main.c. So first in the main.c, we are configuring the LED and I'm calling the external interrupt function. We'll discuss that. Then we have to enable the GIE and there is no logic inside the while one. So coming to the external interrupt, we have to select the edge as a falling edge and we will be enabling the interrupt for the RB0. Then we will be having the ISR function. Inside the ISR function, we need to check whether interrupt is generated because of the RB0 the switch. If so, we are going to toggle that LED and before coming out of the ISR, we have to clear the flag bit to 0. So LED1 is nothing but a macro. The macro is available in the .h file. RD0, I have defined it as LED1 and port D, tris D, all are macros I have taken. And in the external.h file, I don't have anything here. Just I have added the function prototype for the init external interrupt. So whatever the code we have discussed, the same code is available here. So now we'll build the project. Yeah, build is successful. Okay, build is successful, loading is also completed. So now we'll dump the hex file on our board. Interrupt sources, the very first project, external interrupt. So just default protection hex file. Now, whenever we press the RB0th switch, so this switch, this RB0th switch only, we are programming as an interrupt. So whenever I press the switch, falling edge will occur. Whenever there is a falling edge, interrupt will get generated. So we will be toggling the LED. Now you can see I am going to press the switch. So since I have pressed the switch, interrupt got generated and the LED got toggled. Now one more time I am going to press the switch. Now you can see since I have pressed the switch for one more time, interrupt got generated and the LED got toggled. So whenever I press the switch, LED will be toggling. Is the programming is clear for everyone? Now, whatever we have programmed for the polling and whatever we have programmed for the interrupt, almost both the output are same only. Yes or no? While programming for our digital keypad also, both our level triggering and edge triggering was working fine only. Because in case of our digital keypad programming, which code we wrote? Best case code only we wrote. Best case code only we wrote. Now what we will do? Will understand the difference between polling and the interrupt. Okay, so in order to understand the difference between polling and the interrupt, what I am going to do, I am going to use one switch which is connected to RB0. Okay, this switch, okay, I'm going to use the switch as an external interrupt. Okay, and one more switch I am going to use, which is RB1. This we are going to use it as a polling only. This we are going to use it as a polling. So whenever I press the RB0th switch, I am going to toggle the, okay, I am going to toggle the RD0. Okay, and whenever I press the RB1th switch, I am going to toggle the RD1. Okay, I have taken different switches, different LEDs. So whatever the code we have executed for the digital keypad, we programmed on both level triggering as well as the edge triggering. Our code was working fine. But now we'll understand, by adding some extra piece of delay, we'll understand whether actually the polling is missing the event or not. Okay, so we have a sample code for this. Let me open the sample code directly. So in the same interrupt sources, you'll be having the next project as polling versus interrupt. We will be having the next project as polling versus interrupt. Now I'm going to open that project. Let me close all the other files. Okay. So in that polling versus interrupt project, okay, so here I'm using both interrupt also I'm using, polling also I'm using. So since I'm using the digital keypad, I have taken the digital keypad.c file also. This file we already know, and we will be having the ISR as usual and then the main function. So external interrupt.c also we discussed, ISR.c also we discussed, the same code. I didn't do any changes. Now the changes are there in the main function. So we are configuring the LED. I'm using the external interrupt as well as the digital keypad, and then I'm configuring the GIE bit. So now here you can see I'm calling the read digital keypad function on state change. Whenever I press the switch number 2, I am going to toggle the LED2. LED2 is a macro which is nothing but the RD1. Okay, and here you can see I have added a delay. Because of this delay only, the polling, it will be missing the event. Whenever I press switch number 2, the event will get missed. But whenever I press switch number 1, since I am programming that as an external interrupt, immediately RD0 will be toggling. Now we'll dump this code and we'll check the output. So I'm building the project. Yeah. Build is successful. Loading is also completed. We'll load the hex file. So now the second project, polling versus interrupt. Yeah. Now I have loaded the hex file. So RB0 as an interrupt, RB1 as a polling. Now whenever I press RB0, I will be getting the output. So now I am pressing the switch RB0. Yes, LED1 got toggled. Now I am pressing RB1. I have pressed the switch. Is the LED toggled? I have pressed the switch. Is the LED toggled? Is the RD1 LED is on? No. Event has been missed. One more time I am pressing. Now also event is missed. One more time I am pressing. Event missed. So a fourth time I have pressed. Now only it got turned on. So all the previous presses, what happened? All the events has been missed. Because of what? We added some worst case, we added some worst case or the average case code. Because of the delay, it was not working. That is the disadvantage of polling. So we will be missing the event. In order to toggle the LED, I waited for some long time. 4 times I pressed the switch, then only the LED got toggled. So I was waiting for the longer time. I'm not getting the response immediately. I'm waiting for some time, then only it is toggling the LED. But in case of interrupt, whenever I press, immediately the LED will get toggled. We will not get any kind of delay here. We will be getting the immediate response, and we will not miss any kind of event in the interrupt. Is the difference between polling and the interrupt is clear? What about others? Is that clear? Already the code is available in your sample codes. Do you want to make a note of this or shall I proceed with the next one? Do you want to make a note of this? Okay. Make it fast. Okay. First copy this. Once you have copied, let me know. Everyone, have you noted this? Dilip, can you take a picture? Yeah. So now we'll move to the one more coding. Okay. So now we know that uh, polling is having three disadvantage: missing of event, bad response time. That with the help of the interrupt, we overcome that. And we will be having one more disadvantage, which is bad power management. So whenever we use a concept of polling, we cannot put the microcontroller on a sleep mode. We cannot put the microcontroller on a sleep mode. Now, with the help of an interrupt, I am going to use or I am going to put the microcontroller on a sleep mode. So here, okay, I'm going to take one count variable. Okay, I'm going to increment the count variable also. I'm going to increment the count variable. It's almost like a self counter, or automatically it will increment for 5 times. Okay, it will increment the count value. If that count is 5, if the count is 5, I'm going to put the microcontroller on sleep mode. If the count is 5, I'll be putting the microcontroller on sleep mode. Okay, so here, along with incrementing the count, for each and every time, I'm going to toggle the LED. I'm going to toggle the LED. Okay, so for one time count increment, one time it will toggle, one time count increment it will toggle, like that. Okay, so it's a self counter. Okay, and if the count value is 5, I'll be putting the microcontroller on sleep mode. In order to put the microcontroller on sleep mode, we will be having one built-in function called sleep function is available. Microcontroller, it will enter into the sleep mode. Sleep mode means it will not execute any instruction. It will stop executing that instruction. Okay, it will not execute any instruction. So since the instruction is not getting executed, it will not toggle the LED. So once the microcontroller entered into the sleep mode, the LED will get stop toggling and the count will also not get incremented. Okay, now after putting the controller on sleep mode, we are going to wake up the microcontroller with the help of the external interrupt, right? So whenever I press the RB0th switch, external interrupt will get generated. Whenever there is an interrupt, okay, controller, it will execute the ISR. Whenever there is an interrupt, controller will wake up and it will directly go to the ISR. After completing the ISR, then the controller, it will return to the while one. So since the controller is wake up, again the controller will return to the while one. So what it will do, it will increment the count, toggle the LED, and again after 5 times, again it will enter into the sleep mode. So this is what we are going to do. So here just we are going to understand how to put the microcontroller on sleep mode and how to wake up the microcontroller. Okay, now we'll understand this. We already have a sample program. Let me open that code. So it's nothing but same interrupt sources. You will be having the power management code is available. Okay. So let me close the other files which I have opened. Yeah. So in this, as I told, we are using the external interrupt. No changes in the external interrupts. It's same. And in the ISR also, no changes. Now, coming to the main function. Okay. So as I told, it's a self counter. So sorry, it's decrementing I'm doing. If you want, you can do increment also, no issues. Okay, I have taken the count value as 5. So 5 times I'll be toggling that LED, and then I have added the delay also because I'm decrementing the count. It's a self decrementation, it's happening. Okay, so by self it will be decrementing the value until it reaches 0. So 5, 4, 3, 2, 1, 5 times it will be getting executed. Whenever the count value reaches 0, it will come to the else part. Then inside the else part, I'm resetting the count value to 5, and immediately I'm calling the sleep function. So the microcontroller, it will enter into the sleep mode. Microcontroller will enter into the sleep mode. In order to wake up the microcontroller, we are going to press the external interrupt switch. Okay, so I have taken one count variable as 5. Each and every time I'm decrementing that count, along with that I'm toggling the LED. So 5 times I'm decrementing, which means 5 times the LED will get toggled. After the fifth time, count value it will become 0. So it will enter into the else part. So we are going to put the microcontroller on a sleep mode. Now we'll execute this code and we'll check the output, how it is working. I'm building the project. So here it is building. Build is successful and the hex file is also loaded. So we'll dump that hex file on our board. Okay. So our power management code, best default protection hex file. So now once I have loaded, you can see the LED started toggling. I will reset the controller. Now observe the RD1 LED. It will stop. It will toggle for 5 times. On, off, on, off, on. Like that 5 times it will do. Yeah. So now we can see after toggling, it got stopped. Why it stopped means because of after 5 time, the microcontroller, it will enter into the sleep mode. Now we are going to wake up the microcontroller by pressing the interrupt switch. So once I press the switch, microcontroller will wake up and it will start executing the while one as well. So again, only for 5 times it will happen. Observe, I am going to press the switch. Yes. Now the LED is getting toggling. Yes, only for 5 times it toggled and it went to the sleep mode. Now one more time I am going to wake up. Again 5 times on off will happen. Now again it went to the sleep mode. So here this power management code is to inform you like we can put our microcontroller on sleep mode. In order to wake up the microcontroller from sleep mode, we have to use the external interrupt switch. Do you have any doubts in this particular code? Do you have any doubts in this power management code? Others, please do respond. Others, do you have any doubts in the power management code? Since no one is responding today, okay, I will mark it as absent. Only for those who have responded, I will mark the attendance. only those responded. Anusha. Okay. Okay, fine. Okay. So this much is about the interrupt. Okay. So interrupt is completed. Now we'll move to the next peripheral. So now we'll discuss about the next peripheral called timer. The next peripheral is timer. So the timer, it is one of the peripheral. Okay, with the help of this peripheral, we can calculate or record the time. We can calculate or we can record the time. Whatever the time which is running in the real world, can we start or stop the time? Whatever the time which is running in the real world, can we start or stop the time? Whatever the time which is running in the real world, can we start or stop that? No, right? We cannot start or stop that time. But what we are doing with the help of the wristwatch or the wall clock or using the peripherals like timer, what we are doing is we are calculating it, we are recording it. Okay, the same thing we'll be doing with the help of the timer also. We can record or we can calculate the time. Okay, when it comes to the timer peripheral, okay, this peripheral, it will be built in inside the microcontroller. At least one timer will be there inside all the microcontroller. At least one timer will be there inside the microcontroller. By default, one timer will be there. Maximum it can have any number of timers, it depends upon the controller. So timer is one of the default peripheral inside the microcontroller. Okay, now we'll discuss more about this timer. So as I said, the timer, it will be calculating the time. Whatever the time it is calculated, it has to store the time. Whatever the time it is calculated, it has to store the time, right? So in order to store the time, here we will be having the first term, which is nothing but the resolution. Okay, we'll be having the first term with the timer as a resolution. Sakshi, can you unmute?
Hello? Hello?
Yes, Sakshi, what do you want? Sakshi? You were not responding in the class, so I didn't give the attendance. Only 4 or 5 responded. Only for those I have given the attendance. Clear, Sakshi? Yeah. Others, listen. So now, whatever the time it is calculating, okay, we are going to store the time. Whatever the time it is recording, we need a place in order to store that value. So in order to store that value, we will be having a register. We will be having a register. Okay, so in order to store the calculated time, the timer peripheral, it will use one register. This register, it can be an 8-bit register, or it can be a 16-bit, or it can be a 32-bit, like that it can be any bit. So width of the register, width of the register, we call it as a, one second, sorry, I wrote something. Yeah. Width of that register, we call it as a resolution. Okay, width of the register, we call it as a resolution. So whatever the time we are calculating, the timer, it will be storing the calculated value inside one register. width of that register, we call it as a resolution. It can be any bit, like 8 bit, 16 bit, 32 bit, like that. It can be any bit of resolution. Okay, so now let's say I have one 8-bit register. To this 8-bit register, to that 8-bit register, what is the minimum value we can store? What is the minimum value we can store to that 8-bit register? Minimum value I am asking. I'm not asking the maximum value. What is the minimum value we can store to that register? Minimum value is 0. Minimum value is what? Minimum value we can store is 0. What is the maximum value we can store? What is the maximum value we can store? Very good. Maximum value is what? 255 will be the maximum value. More than 255, I cannot store. So 0 to 255 is the range of an 8-bit. Now let's say I have a 16-bit register. With respect to the 16-bit register, same. Minimum value will be 0. What will be the maximum value? What is the maximum value we can store to the 16-bit register? What is the maximum value we can store to the 16-bit register? How will you calculate that? 2 power 16 minus 1. Yeah, 16 minus 1 you have to add. So 65,535 will be the maximum value. This is the maximum value we can store to the 8-bit, sorry, 16-bit register. Okay, so the first term is nothing but the resolution. Okay, and the resolution is representing width of the register. Okay, what is the width of the register? Okay, that we call it as a resolution. Now we'll move to the next term, okay, with respect to the timer. So the next term we call it as a tick. So what is tick? So tick, it is nothing but the process of incrementing or decrementing the register value. The process of incrementing or decrementing the register value. So this we call it as a tick. So now we know that the calculated value will get stored to a register. Okay, now assume I have one 8-bit register. I have one 8-bit register. So once we started the timer, what the timer will do, it will keep on changing the register value. It will keep on changing the register value up to the max. Since it is 8-bit, the maximum value is 255. So up to the maximum value 255, it will keep on incrementing that register value. Instead of incrementing, it can decrement also. If it is starting from 255, it can decrement the value also. Okay, it will keep on decrementing the value up to 0. Okay, so once we enabled the timer, what the timer is doing, it is changing the register value one by one, 0, 1, 2, 3, like that. It will change the register value. The change in the register value we will represent with the term called tick. Okay, so whenever we are incrementing, okay, that we call it as uptick. Uptick means we'll be incrementing. And whenever we decrement, okay, whenever we decrement, that we call it as downtick. That we call it as downtick. So once we enabled the timer, what the timer will do, it will keep on ticking the register. It will keep on ticking. Either it can uptick or it can downtick. Anything it can perform. It depends upon that particular peripheral. Okay, now if the timer register is ticking, means inside the register what value we are having? A normal decimal value only we are having. Yes or no? If it is ticking, ticking means what? It's calculating the time. But whatever the value is there inside a register, it is a normal decimal value. But how I can relate it with the time? Time in the sense we have to measure with the units like nanoseconds, milliseconds, seconds, microseconds, like that only. But once the ticking is happening, the register value, so decimal value is getting incremented. So how we can relate this with the time? For this, we will be having the next term called quantum. Next term called quantum. So what is quantum? Quantum, it is representing the time taken for one tick. How much time our microcontroller is taking in order to increment that register value. So in order to increment that register value for one time, how much time our microcontroller is taking. Now, let's say inside our microcontroller, inside my while one, I am writing the code. We know that whatever the code we are writing, all are an instruction to the microcontroller. Whatever the code we are writing, all are instruction to the microcontroller. Assume I am writing one instruction. Int a is equals to 10. I am assigning one value to the variable a. This we call it as what? One instruction. That we term it as one instruction cycle. One instruction cycle, which is IC. Okay. So with respect to our microcontroller, in order to execute any instruction, the controller, it needs some clock pulse. So how humans are having the heartbeat, similarly the microcontroller will be having the clock pulse. Without the clock pulse, microcontroller, it will not do any operation. It will not execute our code. So in order to execute the instruction, microcontroller, it needs a clock pulse. Microcontroller, it needs a clock pulse in order to execute that instruction. Okay. Now, in order to execute that one instruction, how much clock pulse it is taking? It will be taking 4 clock pulse. 4 clock pulse in the sense 4 high and low pulses will be generated. Okay, what will happen? 4 high and low pulses will get generated. Okay, like this. High, low will get generated for 4 times. So this much amount of time our microcontroller will take in order to execute one instruction. Okay, in order to execute that one instruction, how much time it is taking? 4 clock pulses, 4 high and 4 low pulses. It needs 4 clock pulses of time it will take. Now, fine, in order to execute that instruction, 4 clock pulse it is taking. But now here we are incrementing the tick. So in order to increment one tick, same it will take one instruction cycle of time. Which means in order to increment the one tick, it will take same 4 clock pulse of time. It will take same 4 clock pulse of time. But still we didn't get that units of time, nanoseconds, milliseconds, we didn't get that. So we have to calculate that. So what we are going to do? We are going to calculate the time taken for one tick. So what is the formula to calculate the time? Time is equals to 1 divided by frequency. Time is equals to 1 divided by frequency. So time only we are calculating. What we are calculating here? Time only we are calculating. If we are calculating the time, which means we should know about this frequency. Yes. So we will be having something called operating frequency. So as I told you, the controller, it has to execute the instruction. In order to execute that instruction, it needs some clock pulse. How the clock pulses will get generated? With the help of the internal oscillator will be available. Okay, internal oscillator will be available. That oscillator, it will generate the clock pulse on the defined frequency. at what rate high and low pulses will get generated, that we will term it as frequency. Okay, so the operating frequency of our microcontroller is 20 megahertz. The operating frequency of our microcontroller is 20 megahertz. Yes, the operating frequency is a fixed frequency. We cannot change that. But if you are building your own controller, you can give any oscillator frequency. Okay, inside our microcontroller, in order to execute the instruction, it needs a clock pulse. The clock pulse, it will be generated with the help of an oscillator. So we are having one internal oscillator. Yes, it is fixed, and the internal oscillator frequency is 20 megahertz because it's inside, right? So we cannot change that now. If you are creating your own microcontroller, then you can change that. Okay, for our microcontroller, okay, it is having the capacity, our microcontrollers operating frequency. Okay, capacity of operating frequency, it is actually, it will support up to 40 megahertz. It will support it will support up to the 40 megahertz. Okay, it will support up to the 40 megahertz. But whoever created our microcontroller, they have selected with the 20 megahertz of frequency. Yeah, it is of the internal oscillator. Okay, using external oscillator. So our controller's maximum frequency is what? It is capable to support up to 40 megahertz. So according to that, you can select the external, you can provide the external oscillator. Maximum capacity our controller can bear is 40 megahertz. More than that, controller will damage. Clear? Yeah. So now we know the frequency, and at the same time here we are having the clock pulse also. So to calculate the time, we have to include the number of clock pulse to execute the one instruction. So 4 multiplied by 1 by frequency. So now we have to simplify this. 4 multiplied by 1 divided by frequency is 20 megahertz of frequency. 20 megahertz of frequency. Now what is 4 by 20? We will be cancelling 4 for 1 times, 5 20 will go for 5 times. So we will be getting time as 1 by 5 megahertz. What is the value of 1 by 5? What is the value of 1 by 5? 1 divided by 5. What will be the value? 1 divided by 5 is 5. 0.2. Yeah, so 0.2 multiplied by megahertz we are having, that is 10 to the power 6, but we are having the megahertz in the denominator. So when it comes to the numerator, it will become minus 6. It will become minus 6. Now still we didn't get any units. So and the time it will be representing in somewhat some whole numbers we need, but we are having in decimal. So now I'm going to apply the mathematics here. So here I'm going to add few more zeros. Okay, multiplied by 10 to the power minus 6. So now what I'm going to do, I'm going to move the decimal for 3 times from here. Okay, from here I'm going to move the decimal value for 3 times towards the right direction. I am going to move. So if I move the decimal for 3 times, what will happen? 200 will be there. So before 2 I have the dot, after 2 and one more time means we'll be having the value 200. So 200 multiplied by 10 to the power minus 6. Since we are moving the decimal value to the right side, 3 times I have moved, so we have to add the minus 3. So what will be the time we will be getting? 200 multiplied by 10 to the power minus 9. So 10 to the power minus 9 is nothing but nanoseconds, right? So we will be getting the time as 200 nanoseconds of time, which means in order to increment one tick, our microcontroller, it is taking the 200 nanoseconds of time. In order to increment the one tick, our microcontroller is taking the 200 nanoseconds of time. So now what is the time taken for one tick? Now time taken for one tick is 200 nanoseconds, and at the same time our microcontroller is executing the instruction with the same 4 clock pulse. So in order to execute one instruction, our microcontroller is also taking how much time? Same 200 nanoseconds of time. Same 200 nanoseconds of time. Now if the register value, okay, now if the register value is changed from the 0 to 1, if the register value is changes from 0 to 1, means one tick has occurred. What happened? One tick has occurred. In order to generate this one tick, how much time it will take? 200 nanoseconds of time it will take. Okay, in order to generate one tick, 200 nanoseconds of time it will take. And again, after generating one, again from here it will increment to the value 2, which means what happened? Again we have to add 200 nanoseconds. For two ticks, one more 200 nanoseconds will get added. So based on that we will be calculating the time. So now in order to calculate the time with the help of a register, we need the total number of ticks multiplied by time taken for one tick. Time taken for one tick. Now, if I have an 8-bit register, what is the maximum number of ticks we can store? If we have an 8-bit register, what is the maximum number of ticks will be there for to fill the register? What will be our maximum number of tick? The maximum number of tick is nothing but 255 multiplied by time taken for one tick. Just now we have calculated, that is 200 nanoseconds of time. So if you simplify this, you will be getting the value as 51 microseconds of time. 51 microseconds of time. So if we have an 8-bit register, in order to fill that register, 255 ticks will happen. For that 255 ticks, how much time we can calculate? 51 microseconds of time we can calculate. How much time we can calculate? We can calculate the 51 microseconds of time. Is this is clear? Which one, Shibun, I want to repeat again? It is a formula, Shibun. Time is equals to 1 by frequency is a formula to calculate the time. This is how we will be relating the time and then the frequency. Okay. And all the simplification is a mathematical step only. It's a general formula. For different microcontroller, will the calculate in this way. For all the controller, same formula only. This is a physics formula. We cannot go and change that theory and all. Okay, so the formula is same, the values will be different. The operating frequency, it can vary from one controller to the another microcontroller, and the number of clock pulses to execute one instruction also, it will vary from one controller to the another controller. The values may vary, but the formula will not change. Formula will be same only. Clear? Others, please make a note of this. Once you have noted, let me know. I will scroll down. Yes, that will be available in the data sheet. By referring to that, you can calculate it. Make a note of this also, the remaining part. Okay. So now we'll discuss more about this. So now, once we started our timer, what the timer will do? It will do the ticking, right? So assume I have an 8-bit timer. Okay, whatever we are discussing, it will be an 8-bit. The same process for any other bits also, 16-bit or it can be 32-bit, the same thing. Only the values will change. Okay. So now assume I have one 8-bit register. Once I enabled the timer, we know that it will start the ticking process. Up to 255, it will tick. After 255, if I increment for one more time, after 255, if it is incrementing for one more time, will it go to 256? After 255, if it is incrementing for one more time, will it go to 256? No, right? So at that time, what will happen? After 255, if one more tick is happening, that we call it as overflow. So whenever there is an overflow, the timer register again it will start from 0. So this we call it as what? This we call it as overflow. So whenever there is an overflow, the timer register again it will start from the value 0. So first the register, it will start from 0. It will keep on incrementing up to 255. So 0 to 255, total number of ticks will be 255 ticks will be there. After 255, if one more tick is happening, that only we call it as an overflow, which means we will be having 256 ticks. Now in order to generate one overflow, how many ticks we need? How many ticks will be there? In order to generate one overflow, how many ticks will be there? Up to 255, no overflow. After 255, if extra tick is happening, if extra one more tick is happening, then only we call it as a overflow. So in order to generate an overflow, how many total number of ticks will be there for one overflow? What will be the total number of ticks for one overflow? Total number of ticks, it will be 256 ticks will be generated for one overflow. Up to 255 ticks, no overflow. After 255, if 256th tick is happening, then only we call it as an overflow. So in order to generate one overflow, we need total 256 ticks. Now how to calculate the time taken for one overflow? Time taken for one overflow. The formula is same. a total number of ticks. So in order to generate the overflow, the total number of ticks is 256 ticks multiplied by time taken for one tick is 200 nanoseconds. So in order to generate the one overflow, how much time it will take? 51.2 microseconds of time it will take. So 51.2 microseconds of time is nothing but what? Time taken for one overflow. Time taken for one overflow. Now assume I'm starting the register with 0 up to 255, no overflow are there. Okay, no overflow. So plus one more tick is happening. Now overflow occurred. So to generate this overflow, how many ticks has happened? 256 ticks has occurred. Whenever there is an overflow, after the overflow, again the register, it will start from 0 and it will keep on increment the register value. Now assume the register value got incremented up to 255. The register value got incremented up to 255. Now what will be the latest value available inside the register? So here how many ticks occurred? 255 ticks are occurred, right? Now what will be the value available inside the register? So overflow occurred. Again, the register started from 0. Keep on incrementing. Now I am disabling the timer. Timer is having assume some value 255. What will be the updated value in the timer register? What will be the updated value in the timer register? What value it will hold now? Will it hold the total number of ticks? Will it hold the total number of ticks? Total number of ticks will be what? Will it hold the total number of ticks? Will it hold the total number of ticks? No. Whatever the last updated value is there, that value only it will hold. Which means whenever there is an overflow, whatever the total number of ticks we have calculated, we will be losing all those ticks. Correct? So once we enabled the timer, it will keep on incrementing that register value. Whenever there is an overflow, we have calculated 256 ticks, but whenever there is an overflow, again the register value will start from 0. If the register value is starting from 0, whatever the ticks we have calculated, we will be losing all those ticks, right? We will be losing all those ticks. So now I should not lose the ticks because I am calculating the time. I should not lose those ticks. So what we have to do? What we have to do? We should not lose the ticks. Whenever there is an overflow, we know that register will start from 0. But if it is starting from 0 means we will be losing the ticks, right? So I should not lose the ticks. So what we have to do? We have to store it somewhere. Yes, I have to take a backup. I know overflow will be there. So now inside the while one, okay, inside the while one, I am going to check whether overflow occurred or not. For example, let's say like if the total number of ticks is equals to 256, overflow has occurred. So if the overflow occurred, I have to store it somewhere, right? So now in order to store that, I am going to take one variable called count variable. The count variable, it is representing the number of overflows. Number of overflow. Whenever there is an overflow, what I'm going to do is I'm going to increment the count. Okay, whenever there is an overflow, I will be incrementing the count. Okay, so if count is 1, 1 overflow occurred. If count is 2, 2 overflow occurred. So we will not miss that, right? Now assume above this while one I have some piece of code. Okay, sorry, above this if condition I have some piece of code, and below the if condition also I have some other piece of code. Now it is a concept of a polling, right? So whenever there is an overflow, we may miss that incrementation of the count. Yes or no? We may miss in order to increment that count, right? It's a concept of a polling, right? So here I'm continuously monitoring whether overflow occurred or not, right? So if the controller is executing this piece of code means the incrementation of the count event we will be missing. So now I should not miss any event. So what we have to do? Whenever there is an overflow, I need to immediately increment the count. I should not miss that particular event. So what we have to do? Yes, very good. So that's why we are having what? We are having the interrupt. So whenever there is an overflow, interrupt will get generated. So here first we need to check with the flag bit, right? Example, I'm taking one flag bit, TMRIF, timer interrupt flag bit. So if the flag bit is set as 1, the timer peripheral has generated the interrupt. So before coming out of the ISR, we have to clear the flag bit. That we know. Along with this, I'm going to take one global variable called count and I'm initializing it with 0. So whenever there is an overflow, interrupt will get generated. Whenever there is an interrupt, we will be coming to the ISR. Inside that ISR, I am going to increment the count. Since I am using the interrupt, we will not miss any event. Since we are using the interrupt, we will not miss any kind of event here. Now, count is also having the most important thing, how many number of overflows occurred. For example, let's say count got incremented for 2 times, which means 2 overflows has occurred. Now, while calculating the time, we have to include the count also. So, how we are calculating the time? Total number of ticks. That total number of ticks is based on the resolution. 8-bit timer means overflow will happen on 256. 16-bit timer means overflow will happen on 65,536th tick. So the total number of ticks is based on the resolution. So let me represent that with the R. Next, time taken for one tick is nothing but quantum. So I'll be representing it with Q multiplied by the count. Count is representing the number of overflow. So here the R is representing the resolution, which means it will be having the total number of ticks. And the Q, it is representing the quantum, which is nothing but time taken for one tick. Time taken for one tick. And what the count is representing? It is representing the number of overflows happened. Now based on this, we are going to calculate the time, which means total number of ticks, it will be 256. Time taken for one tick is 200 nanoseconds of time. And the count. So here, for example, I have taken the count value as 2, which means 2 overflow has occurred. So which means how much time we can record? 256 multiplied by 200. The value we already know, 51.2 microseconds. 51.2 microseconds multiplied by 2, which means 102.4 microseconds of time we can record. So whenever there is an overflow, the register value again it will start from 0. If the register value is starting from 0, whatever the ticks we have previously counted, we will be losing all those ticks. In order to avoid that, we are taking one count variable and we are incrementing that count variable, but we should not miss that incrementing that count. So that's why we are using the interrupt here. Up to this, is it clear for everyone? Is that clear up to this? Please make a note of this. Okay, we'll stop here. We'll continue on our next class. Okay, so tomorrow you don't have class. We'll continue from Monday. So thanks for joining. You all can leave. It's already posted in group, right? Saturday and Sunday you will be having the exam. Have you didn't see that message? It's already posted. DS test will be there. Yeah. Yeah, you all can leave. Yeah. Attendance I already marked. Like whoever responded, for those only I have given the attendance today. I already marked that attendance. I have already given the attendance for you, Dilip. Without responding in the class, there is no attendance. Whoever responded, for those I already marked the attendance. You guys can check your attendance in the LMS. Yeah, you all can leave.